put this into discrete form. So saying that, well, next value of x is going to be state transition matrix times parametric x. How do I get state transition matrix in that way? You guys did this in homework, maybe you forgot that you did it. E to the AT. Let's specify T. Let's make it T. That's important. That's the wrong place. So, what's state transition matrix? Exponent M. Matrix exponent of my A matrix times my sample variance. That's my state transition matrix, numerically, for time sample of 0.1. Right? And this will change according to whatever my time sample is. I'm saying I'm running my system at 10 hertz, right? Pretty slow. All right. How can I convert my continuous system to a discrete system? And that actually doesn't point it. At least this discrete system. Right there, the command. C to D. Continuous to discrete. They like to have one numeric it's easier. Are we going from discrete to continuous? What do you think that is? T through C. Okay, so I just put it in my system. And I need a time step. And there it is. Now, this A that says here is really the G matrix that I wrote it. It's a discrete A matrix. Notice it is the state transition matrix that I timed out. B matrix, okay, this is solving the convolution interval for this time step. C matrix and D are what I had before. They don't change. So, what do we have here? We have now write code, actually, just some pseudocode here, for implementing, excuse me, this could be our whole regulator. In fact, here's one of my regulator systems. Right? This is what we indicate back, but I'm going to do this in a primary control. So I'll take D. D. And my times with T. Well, is that. Okay? There's my whole control. Regulator. So that's the state transition matrix for my regulator. B matrix for my regulator. These are actually what? For my C matrix. What are these numbers? What's the C matrix for regulator? Those are the controller gains. Does that make sense? Is my observer trying to estimate what my states are? Multiply by controller gains, I get U. What's the output of regulator? Input to the system, U. Right? But what we have here is, there's our plant. We've got this. This is my R sys. The input is the output of the plant. The output is U In 5200, 6200, remember what ZOH stands for? Zero order volt. What is that? It's basically a device that says, give it this value, keep it there until the next time step. And then it goes to the next one. So it's all basically steps. Well, the zero order. That's what the output of the computer is, a series of steps. So this voltage, you gotta go to this voltage, you gotta go to this voltage, you gotta go to this voltage. Right? This is all built in when I do C2D. All one fell swoop in there. Right. So, how do I actually implement this? So I want code now for this guy. And it's right up here. So look at this. The A matrix says I have three states here, so basically, for state one, we'll call it next. So this means state one next value is equal to, what's my first, 0.814 times x1 present value plus 0.08, whatever it is, times x2, and so forth. Right. Now do x4, or x3. And then I have 1881 times, let's call it U. Okay. And I do that for all the states. Each one of those equations. Everybody see any equations? That's too large. Then my output, y. Well, I found this value, so it's minus 2.3, whatever it is, times x 1, x1u plus minus 2h, 2.3 times x2u. That's the output. Right? So basically, there's 4 lines of code I need to write actually creates this regulator. And all just adding this exactly what it is. Yes?
You calculated the state transition matrix there, but did you actually input it in?
Actually, MATLAB calculated it for me. When I did C2D, it said, take the state transition matrix as my matrix. Basically, it has a code. They know it's that, so put it in. So if you actually look at the code C2D, it'll actually have that statement. If you can read your code, it's pretty cool. What else is needed here? This is actually just regulated, but we need to do what? We need to wrap this and stuff. What do we wrap it in? First of all, I need to read the main of these. Whatever my command for my particular microcontroller is, and that's going to be U. I need to input U for a particular time, right? And then what am I going to, actually, let's see why this is U. Because the input to this thing is Y. I need to read what's the output of my system. Read that to the A to D, calculates all this stuff, and then what am I going to do with U? I need to write that to D to A. Whatever command I have for my particular microcontroller. All right? I'm reading what my output is, do some calculation, write what the command to my program is. That's not all, folks. What else do we need? Well, I need to make sure this thing's running at a very consistent speed. So I need to have some kind of some sort of clock thing here, whatever my command is to keep T constant. Okay. And different microcontrollers do that in different ways, so you have to look at what's the code to make sure this in case is at the right speed. Nice things like V spaces and LabVIEW, they have those kind of commands built in, so you just specify running at this sample rate, and it takes care of that for you. Right, for the microcontroller, you have to figure out how you do that for your particular microcontroller. But we're not done. What else do we need? I just ran this. There, what happens? Runs it once and stops. Right, not much good, so I need to basically go to back up to the start here. So we're doing one of those things that programming class I say never do, endless loop. We're doing an endless loop here. It just continually runs this thing until it stops. Okay. Does that make sense? But we're still not done. Yeah.
I'm just questioning, this system for sensing the states, right? Or estimating?
This is actually the regulator, so it's actually estimating the states and output. So this is our regulator that we have here. So it's this box here. Right. Inputs Y, outputs Z. I don't need to do this because this is my physical system. I don't program that hard. It's a pendulum, like a motor. No, we're just not quite done. One last little thing. How do I start this thing? We continue here. Actually, one thing I need to add before we go to here. I need to replace these values here. So I need to say my present value of x1 is what was the next value. My present value of x2 is what the next value, and so forth. So I need to replace this with what I calculate here for the next go round. Does that make sense? All right. All right. The question is, how do we start this? I need some what? Initial values. So I need outside this loop, x1, maybe it's 0, x2, 0, so forth. Right. Does this make sense what you're doing? It's really not hard to do. It's very simple to program. The one caveat is try to minimize as much as I can multiplying and subtracting, so eventually it's some kind of function here. That's always going to be that number, and calculating this thing. Do that outside the loop. Why? Multiplying takes time. Okay? And all these calculations take time. And what's the slowest thing for a computer to do? If I have my basic operations. Multiply, divide, add, subtract. That's fast. Dividing is the slowest. And then next would be multiplication. And then add, subtract, pretty much the same thing you do to complementary. And then logics are really fast. So be aware that every time I do a multiplication or division, that takes time. I certainly try not to have some sign function in here or something like that. That takes a long time. If it's a constant, I'll calculate it outside the loop. Try to minimize what you're calculating with like groups. This is a caveat. Fortunately, microcontrollers are getting a lot more powerful these days. Used to be they're pretty primitive. They're still not as good as a laptop. No question with this? Can you do a digital, put a controller into a microcontroller? I think probably how it goes. The hard thing is knowing the code of the microcontroller. It's harder than What, Thursday, bring in whatever questions you have, and I'll try to post some old exams on the campus. And the following Tuesday is an exam, right? I'll be here for that. Following Thursday is design day. I know you're all going to be over there showing your nice projects. I'll be over there seeing your projects. That'll be working. As a competition, PTAs for electronics, you know what they're doing? Yeah. Capture the flag again on team 3. Yeah, we want to do fun. What about the freshman design? There's battleship or something. Kind of same thing from ping pong ball work that you do for battleship. Ping pong ball hit this certain stuff. Then she said, "Oh, it's just like a game buy." I go, "Game buy?" I was a kid. We drew up on paper. And, I didn't realize you could buy something. We were usually in the back row of playing battleship or something. All right, Mr. Petro.